Hello everyone, my name is Jeong from Jeonnam National University, South Korea. My presentation topic is the novel Vitreoretinal surgical robot system to maximize the internal reachable workspace and minimize the external link motion. Vitreoretinal surgery is a minimally invasive eye surgery that deals with the retina disease. Surgeon make a small hole and insert a straight, rigid instrument. They perform the microscale tasks such as membrane filling or drug delivery. It requires surgeon's precision, stability, and dexterity. However, this is quite challenging because using a straight needle causes scleral stress, and due to the anatomical constraint, it is difficult to reach the retina without hitting the lens. The microscope positioned above and it restricts the workspace for the instrument, and surgeon's hand trauma can cause the clinical trauma to the patient. So the eye surgery robotic system have been developed. Inside the eye vault, a bendable mechanism was used for higher dexterity. Externally, a double parallelogram mechanism was implemented to make a remote center of motion. We propose a novel system that integrates the concentric tube mechanism and remote center of motion mechanism. Inside of the eyeball, the full DOF concentric tube mechanism is used as an internal motion. It can provide higher dexterity and reduce the scleral stress. Outside of the eye, better driven RCM mechanism is used as an external motion. Since all the mechanism is enclosed, it is compact and clean to use. Our concept is simple but practical use with several advantages. The two systems can compactly integrate it and provide effective and better workspace both inside and outside of the eyeball. As shown in this figure, compared to using the straight tool or concentric tube mechanism alone, the integrated mechanism provides a wider workspace and avoid the hitting lens. At the same time, it reduced the external motion and improved the manipulability by offering sufficient degree of freedom. A concentric tube mechanism consists of pre-curved and spot elastic tube nested inside each other. The overall curvature of the robot is determined by the relative translation and the relative rotation between the tubes. In order to design the specification for the concentric tube and the actuator lengths, we consider the eye's anatomy and surgical environment and required workspace and tool size. We could optimize and miniaturize the concentric tube mechanism actuator for two pre-curved retinal tubes. A driving method that combines needle rotation and translation motion have been proposed in the prostate resection robot. We adopt this driving concept to be used as our concentric tube mechanism actuator for eye surgery procedure. Using 8mm axle motor, tubes can rotate using the small gear and the skewer load, while the translation was achieved with lead screw. Inner component is made of ABS and outer cover is made of aluminum for preventing contamination, and we could achieve the reduced size. The total size is 27, 161, and 32mm, making it more compact than other mechanisms. Better drive mechanisms are generally compact and can create the desired motion effectively. By using BUT, we can generate the RCM motion. In order to integrate with our 4DO app CTM, we choose belt-driven mechanism that provides 2DO app for external tilting motion. The required tilting angle for the eye surgery are 30 degrees for both low and pitch. Since the working lanes need to avoid collision with the patient or microscope, we choose a best link length of 90 and 140mm that can provide sufficient tilting. This is our belt-drive mechanism design. It has a reduced size by using two links with two timing belts and four timing pulleys. We use timing belt to enhance the force transmission, and CTM is integrated at the last pulley. In particular, we were concerned about the accuracy issue due to the hysteresis error from the belt, so we developed the lever-based belt tensioner to adjust the tension. This allows for stable tension to be applied on both sides using screw and provide a better resolution for calibrate the initial position of the RCM. This is our final prototype incorporating concentric tube mechanism and RCM mechanism. It can be adjusted to align the robot's RCM point with the patient incision point using this XYZ stage. Next, we analyze the robot workspace. The Ford kinematics model is obtained using the torsional compliant model that considers both tube bending and the torsional effect. For the inverse kinematics, a Newton lesson-based numerical iteration method is used. We propose a metric called the Reachable workspace. In order to compare the robot's workspace, we need to consider the 3D partial spherical surface. Using X, we determine how much of the retina the robot tip can reach. This serves as a comparison matrix for all cases, whether the needle is straight or curved, and whether the external motion is used or not. Furthermore, when we theoretically calculate the workspace of the internal integrated RCM and CTM, we confirm that the workspace includes the most of the eyeball and can fully reach the retina. We conduct the experiment to evaluate the performance of the proposed system. First, we track the joint trajectory of RCM mechanism using an optical tracking system and the passive IR markers. Using the lever-based belt tensioner, we calibrate the initial position. The results show that there was slight hysteresis at the joint C and D, but RCM point remained almost constant point. Additionally, we validate the accuracy and the repeatability of RCM point through 5 tilting motion. We observe that the angular difference between each link has an error of about 0.08 to 0.35 degrees. The accuracy of the RCM is 245 micrometer, which meet the clinical target accuracy of within 1 millimeter. We also evaluate the accuracy and the repeatability of the concentric tube mechanism. Since our system is intended for teleoperation, repeatability is more important than the accuracy. Using 2 cameras and the electromagnetic system, we track the position of the needle tip following a linear path of 30 mm. The accuracy was 207 micrometer, which is slightly exceeds our clinical target accuracy of 100 micrometers, and the repeatability result shows 246 micrometers error and the 1.029 millimeter of systemic error. It is high accuracy and repeatability, but further improvement is required at this moment. Finally, we evaluate the targeting. We use the plastic eyeball phantom for the targeting experiment setup. The first video shows the integrated mechanism reaching the retina. It successfully reached all the points from A to F with 100 visibility. Additionally, when we use the straight tool with the conventional RCM mechanism as shown in the second video, it can only reach the area between the yellow point. However, when we use the integrated RCM plus CTM mechanism, it can be reached the area between the red point, demonstrating the mechanism provide a wider workspace. Compared to the straight tool, it can reach 89% of the retina and has a 6 degrees of external tilting motion. This emphasizes our mechanism is effectively used to maximize the inner workspace and minimize the external link motion. We are currently developing a deep learning-based kinematic model to address the non-linearity of the robot, such as snapping, to improve the accuracy and the repeatability. It will provide more accurate motion for the microscale surgery, and in the future, we plan to integrate this robot with FPGA-based force sensing module to develop the force feedback telesurgical system. In conclusion, we propose a new CTM plus RCM vitreoretinal surgical robotic system designed for practical use. This system offers several advantages, including the an enhanced workspace. We have validated the system through several experiments, and we are planning to improve it further to achieve sufficient accuracy and repeatability for the microsurgery. We expected that this system have a feasibility to effectively use in the vitreoretinal surgery. I'd like to conclude my presentation. Thank you for listening.